Hello, and thank you for your time. Chipkin Automation System offers a full training course that is free and online. It covers this topic as well as Modbus and BACnet in much more detail. Then we go on to teach you how to install and configure a protocol gateway. We will provide a free gateway that runs on Windows machines. Please look in the video description for a link to our Chariot course. In this video, we will give an overview of what to expect in the course. To start, we are looking at getting some data from an energy meter. The meter supports Modbus TCP but does not support BACnet. This is a common problem. It could be an energy meter, a fire alarm panel, a chiller, a thermostat. Using a gateway allows you to connect foreign devices into one operational system. The site needs the energy data in BACnet. In this example, we're going to use BACnet IP, the Ethernet flavor of BACnet. There is also a serial flavor called BACnet MSTP. Most of this video could apply to both flavors of BACnet. So you have data which is available in Modbus, and you have a BACnet system that you want to consume or monitor the data for control and reporting purposes. How on earth do you connect them? Well, they both seem to use Ethernet, so perhaps an obvious answer is you connect them using Ethernet cables. While Ethernet might carry some packets of data, that answer is only partially correct. You must then ask yourself, how does the BACnet system request data? How does the meter respond to requests for data? What data specifically? How often should I read the data? There are lots of considerations. I am reminded of the joke about Mr. Modbus and Mr. BACnet. They meet at a party, and Mr. Modbus says to Mr. BACnet, "It's good to meet you." Mr. Modbus doesn't understand him, and he answers, "What?" They have no idea what the other is saying. They might as well be talking foreign languages, which is exactly what they are doing. Not only do the two systems talk in different languages, the one talks Modbus and the other talks BACnet, but they also do not address data the same way. Think of yourself in Paris on holiday and you can't speak French. It's going to be tough. But at least in hotels in Paris and New York are addressed in similar ways. Number 1 Rue de Sol, Paris, France. Number 1 Fifth Avenue, New York. Now imagine you go to China. It gets harder. We have the same kinds of problems when we try and connect foreign devices like this Modbus energy meter with a BACnet building system. You need a gateway because the protocols are different, the messages are formatted differently, and data is addressed in different ways. Modbus knows about 40,001 but has no idea what analog variable 1 is. BACnet knows about AI, AO, AV but hasn't got a clue what 40,001 or 30,001 mean. This is a sample from the manual of the Modbus energy meter. It comes from the section of the manual which tells you about what data is available using Modbus. In this sample, you can see that we are told the register number, the engineering units, a description, the data type, and some scaling information. This points to one of the huge differences between Modbus and BACnet. Unless you find the manual with the points lists, like the one shown in this sample, you are left in the dark. There's no way to get this information from the device. Modbus does not have a system of reporting this information. BACnet does. It's called a discovery service. Enough about the difference between Modbus and BACnet. Let's bring our focus to how to get the Modbus data into BACnet using a gateway. Think of the cache as a bucket or box, a place where you can store stuff. For example, the total real power or the frequency that we are interested in. These storage locations can store different types of data, numbers, characters, bytes, bits, floating points, integers, or long integers. Sometimes it's convenient to have an array of storage locations. Keep in mind there can be more than one cache. Each will have a unique name, each might store different data types, they might be different lengths. The data caches have 3 key properties, but there could be more. And they could be complex structures. BACnet objects are complex structures. The value of the object is just one element of the structure, known as the present value. But BACnet objects also have other properties, like the object name, description, and engineering units. Here we made a data store that is an array of 5 items. They have been defined so they can store floating point numbers. That is the choice we made because it's appropriate for storing power and frequency. For example, the frequency might be 59.9 Hertz and the power might be 130.5 kilowatts. We have a numbering system to refer to each of the 5 storage locations in our array. We have numbered them 1 to 5, but we could have numbered them 0 to 4. Typically, the numbering system is a choice forced on us by the product we're using. Since we've defined storage locations, let's discuss another topic. How do we get data from the energy meter into the cache? At a guess, we need to work out what data we want, how it is addressed, and then we're going to have to define a task to take the action of reading the data we want and storing it in the cache location we have chosen. An energy meter can contain lots of data points. For example, it might have the current, voltage, power factor, and energy consumption for each phase, and it might have the overall power factor and energy consumption as well. The meter might have some status data to report if it is in a fault or not. The data you need is dependent on your project needs. Sometimes a project wants almost all the data available, and sometimes it wants specific data and doesn't cloud the issue by integrating other data points. In our project, the customer has stated that the 2 points he's interested in converting to BACnet are the total real power and the frequency. The total real power is available in Modbus Register 40003, the frequency in Modbus Register 40010. We also note the data type and scaling. Modbus can only carry whole numbers, so if you want to be able to store a frequency of 59.9 in a Modbus register, you need to store the number 599 and tell the customer/consumer of the data to divide by 10 to get the actual frequency. And you can see the scaling factor is 10 on the data sheet. An aside, if you look in register 40008 and see the value 1000, then it means there is 1.000 amps. Scaling is 1000 in this case. Now that we have identified the data, we need to integrate into the gateway. We must also define a cache in the gateway to store the data. It takes effort to get the data. Task is a good word for it. Modbus is a master-slave type protocol. That means a device like the energy meter does not spit out energy data without being asked. It is the slave. It does nothing until it receives a message from the master. The message contains instructions like read or write. They also contain addresses for which data is needed. There are 2 data items, so in this example we are defining 2 tasks. Can you see the possibility that we could compress this into one task? Something like read 8 items starting at 40,003, thus reading 40,003, 4, 5, 6, 7, 8, 9, and 40,010. Thus including both points we were interested in. Part of the definition of a gateway task is to tell the gateway where to store the data that is read. If we were writing instead of reading, we would still need a cache location. That location is where we will extract data to send the remote device. What we don't show on this page is that each task only reads one data item. For example, the length equals 1. We know we want to read this data from the energy meter, but we need a more technical answer to the question, read from where? These devices have IP addresses, and Modbus slaves also have node IDs. The node ID is usually 1, but there are exceptions. Usually there's only one device behind an IP address, but that isn't always true either. A device can contain multiple virtual devices inside it. That would mean that there would be one IP address but many nodes. Modbus node IDs are integers, mostly starting at 1 and running to 247. That's what the rules say, but some devices break these rules. For our current project, there is a single simple device, an energy meter. It has an IP address and the node ID is 1. Where did we get this information? One place we might have found it is in the manual, or these might be the default settings for the meter. Even if they are the default settings, They might have been changed when the meter was installed on site. Ultimately, you need this information from the person who installed or configured the meter. You might make a note now that you should check this information when you install the gateway. Now that we have a more complete definition of the tasks at hand, we must define how to read the two data items we want, total energy and frequency. But what would happen if we used the wrong IP address? We almost certainly would not get a reply to the message we sent. These errors are often called timeouts. We send a message, wait a time, and then give up, although we may choose to retry a few times before finally giving up. Parameters such as the duration of the timeout, the number of tries, and how often to retry are often configurable parameters when you create the task in the gateway. The same discussion applied to the node ID. If we have the correct IP but the wrong node ID, we will also get timeouts. How often? This is often a configurable parameter in gateways. It is not that important with Ethernet protocols, but it is with serial protocols, where the bandwidth is much lower. If you have limited bandwidth, it is recommended that you configure your tasks so that you read the most important data most often, for energy data is not that critical. Also remember, just because we read the data using Modbus and store it in our cache often, that does not mean the BACnet system will always have the latest and greatest. The BACnet building system also needs to be configured to read the data from the gateway often enough to keep it up to date. Keep in mind, not all gateways allow tasks to run as often as possible. Some don't give you the control of this at all. However, our gateways allow control. Depending on how many tasks you have defined and how often they execute, there may be some variance. If I have 1,000 tasks and each takes 0.1 seconds to complete, then only 100 tasks can be executed per second. So if I set the task frequency to a number like 0.5 seconds, then you can see the problem. The large number of tasks overwhelms the ability to execute them all every 0.5 seconds. It is more like each task can only execute once every 10 seconds. Now we're going to talk about the flow of messages and data. As we mentioned before, Modbus is a master-slave protocol. Slave means passive. It waits, doing nothing until asked or commanded. That is the job of the master, to do the asking or commanding. Since we have defined two tasks, let's look at task 1. Read 40003 from node 1 at the IP address 192.168.1.168 and store the data in a cache called meter_data at offset equals 1. Do this task continuously as often as possible. The gateway is the Modbus master. It wants the data. It sends a message to the Modbus slave energy meter. The message is addressed to the correct IP, to the correct node, node 1. It asks for the data from a single register, 40003. Modbus can read up to 108 items in a single message, but for this task we are only reading 1. A message from a master to a slave that reads data is often known as a poll. The message arrives at the slave because it has the correct IP address. The slave looks to see who the message is addressed to, in this case node 1. The meter checks, I am node 1? Yes, therefore I will accept the message. If it didn't accept the message, say because it was node 2, the meter might ignore the message or respond by reporting an error. An example of such an error could be defined as device unknown. Usually these errors are reported by reporting an error number, and then you must look up that error number in the protocol specification document. For this example, let us assume the message is addressed correctly. Then the meter will evaluate or parse the message, breaking it down into its elements. Are you reading or writing? How many items of data? What is the starting address of the data that is wanted? In our example, we are reading a single item starting at 40003. The energy meter now validates the message elements. Do I support read? Yes. Do I know if I have registers? Do I have register 40003? Again, if this validation fails, then the energy meter might send a Modbus response reporting an error, or might just ignore the message. In our example, the energy meter does know about 40003. It extracts the data associated with that register, packs it into the response message, and sends the response message back to the gateway. In our example, the value being reported is 100. Keep in mind that during data requests, the energy meter might not respond at all. It may respond with an error, or it might respond with the data that was requested. When the response arrives at the gateway, the data will need to be validated. Is the message intact, or has it been corrupted during transmission? Is the message reporting an error or data? The gateway makes this evaluation. If the message is intact and carries data, the data is then extracted and stored in the cache at the location we defined in the task 1. And thus the gateway stores the value 100 inside the data cache called metadata at offset 1 in the array of storage locations. We have a similar process for task 2. All that is different is what we register we are reading and where we store the value. There is one other small difference. The tasks don't execute at the same time. Task 1 runs as often as possible, but task 2 runs every 5 seconds. Task 2 stores data in a cache in offset 2. In our example, the meter applies with a data payload of 600. The gateway asks, what is the value of register 40010 in device number 1 at IP 192 plus 168 plus 1 plus 168? The energy meter responds, the value is 600. Let's do a quick recap. Our customer has installed an energy meter that supports Modbus TCP at the site. He has highlighted from the energy meter points list which data points he wants. We have configured the gateway to read the 2 data items he wants and define where to store them on the gateway. We read the total power and store it in cache offset 1. We read the frequency and store it in cache offset 2. Let's go ahead and deal with the small issue of scaling. The energy meter's manual shows that the frequency has been scaled by a factor of 10. When we register 40010, the meter applied with a value of 600. What it really means to tell us is 60.0 Hertz. The problem is that Modbus can only carry integers, which is why they use a multiplier to make a whole number. We must do the opposite when you receive the number 600. We must divide it by 10. Therefore, we need to scale the one value before serving it on BACnet. There are 3 approaches. 1. Apply scaling on the read task so it stores the scaled value. 2. Apply scaling when we serve the value, extract it from the cache. 3. Create a task to take the value in the cache, scale it, and then store it in a new location in the cache. Depending on the gateway you're using, some or all of these methods are available. We will come back to this issue later. Now we must configure the BACnet side of the gateway. Let's look at the first question. Did the customer constrain us? Just like we needed to know what the IP address and node ID of the energy meter was, the BMS will need to know the IP address of the gateway. The BMS will also need to know the node ID of the gateway. And just like we needed to know the data objects and the addresses to read the relevant information from the energy meter, the BMS will want to know what the data objects to read in the gateway. We can make all those choices, or the site/project might make those choices for us. They could assign the IP address we use or the node ID. In BACnet, the node ID is known as the device instance number. If you aren't sure of the answers, proceed anyway and simply alert the site to the choices you've made and how to change them. Now we are getting to the key concept of gateways. The items in the cache can be seen from 2 perspectives, the Modbus perspective and the BACnet perspective. The same cache can look quite different in each protocol. From the Modbus perspective, we have the data from 40003, the total power stored in cache offset number 1. From the Modbus perspective, we have the data from 40010, the frequency stored in cache offset number 2. Now let's look at the cache from the perspective of BACnet. The BMS wants to read this data from the gateway, so it must send read data requests to the gateway. But the BMS doesn't know where to send the messages to. It doesn't know the IP address of the gateway. It doesn't know the node ID or device instance number of the gateway. More importantly, it does not know the address of the data objects inside the gateway. First, we will need to assign an IP address to the gateway, and we also need to assign the device instance number. BACnet has its own weirdness. For example, a BMS can only read data from BACnet IP devices that are on the same subnet. Modbus does not have this limitation. You are the best off assigning an IP address that puts the gateway on the same subnet as the BMS. The node instance number is not that important, but it must be unique for the whole site. Since the customer did not constrain us, we will assign arbitrary values for now. Note that we might need to change them when this gets to site, though. In BACnet, we talk about the device instance number, which is the equivalent of the node ID in Modbus. Remember, the BACnet device instance number must be unique for the whole site. So, someone must oversee that. Generally, it's the BMS project people. The Modbus node ID must be unique for serial Modbus, i.e., when Modbus devices are connected to a RS485 trunk. So we have an IP address for the gateway assigned now. We have also assigned the device instance number. Now the BMS knows how to address the messages it sends. For example, send a message to the BACnet device number 389001 at the gateway IP address of 10.10.122.10. But from the BACnet perspective, it doesn't know how to access or address the individual data items, the items stored in the gateway, the total power and frequency. In fact, if you think about it, there is a huge question pending. Huge. How does the BMS know what data the gateway can serve? When it came to Modbus, we had quite a complicated process. We had to find the manual for the device. In the manual, we had to find the section called the Modbus points list. You may be asking yourself, if Modbus has a points list, does BACnet have one as well? Yes, it does. In BACnet, we call the points list an object list. But a gateway has no BACnet objects until you create them. Once you have created them, you can print it off and send it to the BMS people. Or, once your gateway is installed, the BMS people can discover the device and its object or points list. We are configuring the gateway, so sticking to the subject, how do we make BACnet objects? And do we want to create the objects and connect them to the Modbus data we stored in the cache? A Modbus point is simple data object. It has two properties, its address, example 4001, and a value, for example 600. A BACnet object is a complex object. It has many properties. The one we know best is called the present value. Another is the object name, another is the object type. Then we have the object instance number, object number for short. Since we must serve two integers, the total power and frequency, it seems sensible to select analog objects for BACnet, and since they are read-only objects, we should probably select analog input type objects for BACnet. Said another way, we should associate the total power and frequency with BACnet analog input objects. Analog input objects also have object numbers. Let's choose to start at object number 1 or analog input object number 1. We want to associate that with the frequency. That allocation to frequency and the object number is a random or experienced decision. I could easily have chosen to start my allocations with the total power and with analog input number 99 or even 40003, but nonetheless I chose to start with frequency and analog input number 1. So the main point here, the key point, is that I allocate analog input 1 to cache offset number 2 because that is where I stored the frequency, and as I said, we are starting with frequency. So the outcome is that we have allocated the BACnet object analog input number 1 to the data cache offset 2. When someone asks for the present value of the frequency, we will extract the value found in the cache at offset 2 and respond. Technically speaking, the BMS will ask to read the present value of analog input number 1.
it doesn't actually send a request for something called frequency. Continuing in the configuration, we create a new BACnet object. We allocate a type and a number, analog input number 2. We connect it to a storage location in the cache. This time we are doing the total power, so we connect object analog input number 2 to offset 1 in the cache. We use offset 1 because that is where we stored the total power when we configured the Modbus side of the gateway. Completing analog object number 2, we allocate and name the engineering units. The name and units we got from the Modbus points list. So now we have a BACnet objects list. Analog input number 1 is named for frequency in hertz, and analog input number 2 is named for total power in watts. However, we never solved the scaling problem. For the frequency, we saw that the number served by the energy meter is multiplied by 10. When the meter serves the value of 599 for register 40010, it means 59.9 hertz. I suppose one way to fix this is to change the engineering units of the BACnet object to 10 times hertz, but that is not permitted by BACnet since it has a limited selection. So now what? We need to take the value of 600 and divide by 10 before we serve it. Another task is needed. Not another task to read the energy meter, but an internal task, like a script, to do a little arithmetic for us in this case. In gateways, these types of tasks have various names. One common name is a mod for a modification task. So let's define mod task 1. It should do the following. Take the contents of cache offset 2, divide by 10, and store the result in offset 3. Do this continuously. Now we read the frequency scaled up by 10 from the energy meter and stored this value in offset 2 of our data cache in the gateway. Now we take that value from offset 2, divide by 10, and store the answer in offset 3. If the energy meter responded with 599, then we would see 599 in offset 2 of the cache and 59.9 in offset 3. Now you can see why I chose floating point when I created this cache. Even though the Modbus points list said integer, we could deduce from the scaling column that we were going to be dealing with real numbers. It doesn't make sense to create a third BACnet object. Why would we want to have the frequency twice? Thus it makes sense to change the BACnet mapping. By changing the mapping, I mean changing the connection from the definition of the BACnet object to a storage item in the cache. Up until now, we allocated analog input number 1 with the name equal to frequency and the units equal to hertz to cache offset 2. Let's change the allocation to offset 3. Now we have analog input number 1 allocated to offset 3 in the cache. So when the BMS reads analog input number 1 from the gateway, it will get the correctly scaled frequency. Remember how I said we made a random choice to create object 1 and 2 as opposed to random choice of 1 and 99? Well, experience can help you make choices that are less random and more helpful. If you number the BACnet objects the same numbers as the Modbus registers, then when you read analog input 40003 and you get an unexpected value, you know in your troubleshooting to look in register 40003 in the energy meter. There is a much more detailed course with a hands-on training exercise with a real gateway you can have for free. There are also detailed instructions on Modbus and BACnet. The gateway we provide runs on a Windows box, so you could install it on a latte pan board for about $99 and have a real working gateway, or run it on a virtual machine or on your server. If you're interested in learning more about our Chariot Gateway course, click the link in the description below. Chipkin has been at this protocols game since October 2000. We know what we are doing, we are reasonably priced, and we do custom solutions when your project needs them. Thanks and bye.